Hi everyone! Today we are going to prove that the function x squared is continuous on R. So, for that statement to prove, we need to work with the definition of continuity. And suppose we have a function from D to R. That function is said to be continuous if for all a in our domain, for all arbitrarily given epsilon greater than 0, there exists the delta greater than 0 such that the absolute value of x minus a is less than delta, and that implies that the absolute value of f of x minus f of a is less than epsilon. So basically, if you have such a statement with quantifiers, you need to find that one that exists. So because the other ones are given, and based on them, you need to find delta. Okay, let's go to the proof. Write down proof. And there are some magic words that you can use to construct your proof statement. And those are given arbitrary epsilon greater than 0, choose delta. But actually we have to calculate this. We don't know what delta is right now, but we can make some prediction. As I said, based on this statement, for all a in day, for all epsilon greater than 0, there is a delta. Our delta should depend on everything on the left side in the statement. Those are a and epsilon, and we have to ensure that our delta is greater than 0. All right, let's go further with the definition, and that is, suppose we have the absolute value of x minus a is less than delta, but also greater than 0. We have to ensure that that it cannot be 0, because we don't want this. We don't want x equal a. We want unequal, and that implies, then check, we plug in the functions, and at this step we don't write less than epsilon, but rather we factor this expression and see what happens. And this happens. No, but this leads us to a side note that is really important, and at this step we will choose one of the values for delta. And let's say by this part, we know that x minus a, let's estimate one of the expressions from these two, and let's say we work with the one that is given in the statement, and that is x minus a should be less than some delta, and let's say we pick 1 because 1 is easy to handle. And then we write here the minimum of 1 that we got so far, and let's make an observation, and that is okay, we estimated x minus a, and now we need to estimate x plus a. And if we compare them together, we see that their differences are actually to a. And if I write x plus a as the absolute value of x minus a, this guy, plus 2a, so these are the same, but with this expression, we know by the triangle inequality that we can write that as x minus a plus absolute value of 2 times a, and we know that this guy is strictly less than 1. 1 plus 2 times absolute value of a, and so we found an expression for x plus a as well as for x minus a. And let's plug that into this equality. Then we get that this guy is less than delta by the definition, right? we have this less than delta times what you can now substitute for x plus a, and that is 1 plus 2 times a. And we're still at the conclusion of our implication, right? And that guy should give me the epsilon. And we're almost done. We have to calculate delta right now, and that is delta is equal to epsilon over 1 plus 2 times absolute value of a. And we make some square and finish. Okay, let's go briefly through the whole proof again. We had a claim statement that x squared is continuous on R. For that, we need to apply the definition for continuity, and that is said for all a in our domain, for all arbitrary given epsilon greater than 0, there existed delta. That means that we have to calculate somehow a delta that depends on epsilon and a and is greater than 0, and such that absolute value of x minus a less than delta implies f of x minus f of a less than epsilon. And we need to actually work with these two pieces. And then we have these magic words that I want to underline for you guys. This is actually a suppose. And then check. So, and then yeah, we estimated, suppose by the definition given absolute value of x minus a less than delta, also greater than 0. This is because you want to ensure a region, a delta region that is contained in your epsilon tube, so to say. And then yeah, and then plug in the functions, factor the expression, do what you can do with this expression. Like if you write down x squared minus a squared, so you can factor this randomly and then estimate it. And yeah, we know that this part of these two terms is less than delta, strictly less than delta by the definition, and that was the step that we have to estimate also x plus a. And we made our side notes. And yeah, we picked one of the delta values to work with it to come up with the final version of delta, and that is it. All right, let's make an example with actual numbers. And I personally found the square root situation to be the most helpful for me, so to understand such statements. And as earlier we have given epsilon, we need to choose delta. We need to find this, and then we will work with the definitions, and that is in this case our a number associated with this 2, and that is, let's say, suppose x minus 2 is less than delta, and then we plug in the functions, and that is, check, we have the absolute value of square root of x plus 7 minus 3, and the trick to come up with an estimation is to multiply this guy by its conjugate. And we have a fraction of the conjugates, and that is square root of x plus 7 plus 3, and also the same in the denominator, and that is absolute value of it. And if we multiply them, we get x plus 7. So the square root cancel, and minus 3 times plus 3, that gives me minus 9 over. And okay, let's write this also in the absolute value form. And this guy gives me x minus 2 over still this guy, and based on our assumption that absolute value of x minus 2 is strictly less than delta over this guy. And yeah, we are almost done, but we need to estimate this guy further on. And let's say I can omit the absolute values because this guy is always going to be positive, right? And if we want an expression which is greater than this guy, then we can just take delta over 3, right? Because as the denominator grows, the fraction gets smaller and smaller, and yeah, this guy is greater than this guy, and this should give me the epsilon. And what should delta be in order that this equality holds? Well, delta needs to be 3 epsilon. And proof. Yeah. You choose it to be 3 epsilon, okay? And I have to admit that 3 epsilon looks really cool. Thank you for watching. Alright, to illustrate why we always choose the minimum of 2 deltas, let's consider the same graph for a given epsilon equals 0.5. If you plug that into our situation to calculate the x value and solve for x, let's say x plus 7 equal, let's say 3 minus epsilon, which is 2.5. And if you solve for x, you get x equal minus 0.75, and let's say that is x1, and let's say plus 7 equal, let's now 3 plus 0.5, and this is 3.5, and x turns out to be 5.25. Let me check that out briefly. Yeah. Okay. And if we draw these two values for x in our x-axis, then you see that the first delta is going to be 2.75. That is delta 1, and the delta 2 is going to be 3.25. Like this distance and this distance. And you see that both are in our epsilon region, and if you don't take the minimum and go for the greater one, assume we go this distance in the negative direction, then we get minus 1.25, and it might happen that you are not in your epsilon region anymore. Therefore, always take the minimum of these two values. Yeah. Thank you for watching.